Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 3.2, day 2, entitled Polynomial Functions and Their Graphs. And today we're going to talk about the last two objectives. We're going to talk about the shape of a graph near its zeros, and we're going to talk about the local maximum and minimums of a graph. Okay, now, yesterday, or in the previous section, we spent a lot of time talking about the even and oddness of the degree and how that affects the shape of the graph, what the leading coefficient does to the shape of the graph, and we talked about x and y intercepts and domain and range. But here's one other characteristic that we need to talk about. And this is when you have a solution or a zero that occurs more than once in a polynomial. So this would be if you have a situation where you have, x minus 2 squared in the polynomial function somewhere. Technically, x minus 2 would be a factor twice. So that means x equals 2 is a solution, but it's a solution twice. Now we don't graph it twice, okay, but we say that it is a zero of multiplicity for that function, meaning that it's a zero, but it occurs multiple times. Now, there's a couple characteristics about that multiplicity that we need to pay attention to, and that's in this statement right here. It must be important because it's bold and it's italics. Okay? It says, by considering test points on either side of the x-intercept, we conclude that the graph crosses the x-axis at C if the multiplicity is odd. So it's going to cross through C if you have an odd multiplicity, like x minus 2 to the third. That's an odd number. And it does not cross the x-axis if the multiplicity is even. So if you have an even multiplicity, then it's not going to cross the x-axis. If you have an odd multiplicity, then it will cross the x-axis. So if we drew this graph at x equals 2, I don't know what the other parts of the function would be if it's, even or odd altogether. But if the graph came down and then went back up, it means it's going to touch at 2, but it's not going to cross. But here, since it has an odd degree, the graph would cross through that point. Okay? So that's another important feature that we need to make sure that we explore, especially when we get really complicated polynomial functions that we need to graph. So this is the book's table that explains what was on the previous slide. Okay? So if your multiplicity is odd, you are going to cross the x-axis, and there's lots of different ways that it could do that depending on the shape of the graph. Okay? And if the multiplicity is even, then it's not going to cross the x-axis. So it'll touch at that 0, but it won't actually cross through it. Or it won't cross the axis. Okay, so let's take a look at this. Example 8, they want us to graph this polynomial. And we have x to the 4th times x minus 2 to the 3rd times x plus 1 squared. Now, that's a big polynomial. It's already factored for us, so that's good, okay? And since it's already factored, we can find our solutions or our zeros or our x-intercepts right away, okay? Since it's already factored, I know that my x-intercepts or my zeros or my solutions are going to be x equals 0, x equals 2, and x equals negative 1. Those are going to be my solutions. Okay? Now, overall, this polynomial doesn't have degree 4. Okay? Its overall degree would be whatever it is if we multiplied all of those out. So I'd have x to the fourth, and then I'd have an x squared, or I'm sorry, x to the third term, and then I'd have an x squared term. So if I actually factored and multiplied everything together, FOILed it all out, I would get 4 plus 3 plus 2 is 9, x to the ninth. So that would be my overall degree. Now that's important to know because that tells me I have an odd degree. 9 is odd. So I have an odd degree. And remember, that means that the ends are going to be going in opposite direction. And I would have a positive lead coefficient. So all of these x terms are positive, so I would have a positive lead coefficient. So that tells me that the right end is going to be going up. So already I'm able to analyze a little bit of this graph. I know it's got 3 zeros. I know the ends are going in opposite directions, and the right end is going to be going up, so then the left end is going to be going down. Now let's take a look at those new characteristics that we were just talking about. For my x-intercepts, I have x equals -1 and x equals 0 and x equals 2. And those are just my values from up above here. Now, the -1 comes from this part right here, the x plus 1 squared. Now that has an even degree, so that's not going to cross. So the graph is not going to cross the x-axis at -1. It'll touch -1 either from the top or the bottom, but it's not going to cross. Okay, the x equals 0, that comes from the x to the fourth part, and that x to the fourth is also an even degree. So again, the graph's not going to cross the x-axis at 0. It'll touch it, but it's not going to cross it. And the x equals 2, that came from the x minus 2 to the third. So that 3 is an odd degree. So that means my graph will cross the x-axis at x equals 2. So if I just start to draw a rough little sketch of my graph, I'm just going to draw it by hand before I do my actual table of values. Let's see, I've got 0 and 2 and -1 that are my solutions. I know that the right end needs to be going up and the left end needs to be going down. So I know I'm going to start down low on the negative left side of the graph, and I'm going to approach the -1, but I'm going to touch it, but I'm not going to cross it. And then I'm going to have to go over to the 0, but I'm going to touch it and not cross it. Okay. And then I'm going to have to go over to the 3, I'm sorry, to the 2, and then that's where my graph will finally cross. So that's just a really rough sketch of what the graph could look like. So now if I go back and actually make my table of values, I would type that into my graphing calculator, type in this original function, just the way it looks. Okay, leave the parentheses there. Don't multiply it or FOIL it all out, just type it as it looks. I want to make sure that I include the -1 and the 0 and the 2, because those are my solutions. And then I want to point to the left of the -1, so I would need -2, something between -1 and 0, so I need -1/2, something between 0 and 2, so I can do the 1, something to the right, so I need a 3. So those are going to be the values that I want to focus on. Okay, so I have my zeros, and then I have test points on either side and in the middle of all of those actual zeros. Now, in the graphing calculator, we get some really crazy values right away. Okay, and again, if you need to, for this fraction, change your table of values in your calculator, or substitute -1/2 back into the original function. And 3 gives us another crazy value. Okay, so obviously -2, -1024 is not going to be on my graph. But these other values I can put on there. So -1, 0, okay, got that. -1/2, -0.2, so just a little bit below. 0, 0, -1, -4. So I come down about there, and then 2, 0, and then 3, 1,200 is going to be way up there. So my graph now is going to look a little bit more structured. I know how far down I dip now here for that value, and then I go way up to the top. Okay? So you can see how where I put the little dashed line for like what a rough sketch of my graph might look like, it was fairly close. Okay? I wasn't sure how wide or how narrow to make each end. I wasn't sure how far down to make this little dip between the 0 and the 2, but now I know some of that structure. And there's the nicer book graph. Okay, so again, you can see how shallow that first little dip is, and then how the second dip kind of goes down. It actually has a little bend or a little bubble there too before it goes way up. Okay, so use that new feature of knowing the evenness or the oddness of the multiplicity, and that will tell you whether or not your graph should be crossing the x-axis at those zeros. Okay, we have a couple more concepts. We're going to talk about local maximums and minimums, or maxima and minima. And we've talked about this before with our other graphs. You know that when we're dealing with a graph that has curves like this, the high point is going to be your maximum, the low point is going to be your minimum. They call them local just because it's what you can view on your viewing rectangle. Again, we're not worried about any of these extremes where the graph goes forever towards positive infinity and negative infinity. We're not worried about that. Technically, positive infinity would be the maximum value, but we want to focus on that part that we can see. So that's why we call it a local maximum or a local minimum. Okay? And when you're talking about the local maximum and the local minimum together, that's called local extrema. So you might see that in your homework or on a quiz or a test. So when it says to find the local extrema, that might mean to find both of them or only one of them, depending on the type of graph that you're working with. Now, there is another characteristic to keep in mind. When you're dealing with the extrema, there's this cool feature that if you have degree n for your polynomial, so that could be 3, 5, 9, 1800, whatever that degree is, then the graph can have at most n minus 1 extrema. So that means the total of your maximums and minimums will be whatever that degree was minus 1. So if you have x to the nth, then you can only have 8 extrema total. So that's good to know. If you're trying to find all of them, you want to make sure you have the right amount. Okay, so again, a polynomial of degree n can have no more than n minus 1 local extrema. So let's take a look at that in example 9 here. Determine how many local extrema each polynomial has. So for part A, I have all of my terms in descending order already. If it wasn't in descending order, you'd want to rewrite it so that it is in descending order. So that way you can tell that I have a polynomial of degree 4. So 4 minus 1 means I'm going to have 3 local extrema. Now I don't really know if they're maximums or minimums. So let's think about that for just a moment here. Let's use some of those characteristics and figure out how many are maximums and how many are minimums. Okay. I have an even degree, so that means that my ends are going to be the same. They're either both going up or they're both going down. I have a positive lead coefficient, so that means both ends are going to be going up. So how would I draw that? How would I draw a graph where both ends are going up and I'm going to have 3 extrema? That means I have to have 3 curves in it. and we don't know exactly where my zeros would be, so I'm not worried about that here. I'm just kind of mentally thinking of what this graph might look like. But both ends have to go up, and so I'd have to have one curve, and then another curve, and then a third one, and so that my other end goes up. So I'd have to have two minimums and one maximum for this graph. But 2 plus 1 is 3. So 2 minimum and 1 maximum. Okay, so I found out a lot of information just by looking at the function without even typing it into my calculator. Okay, so part B, if I have this function, again, it's all in descending order, so I don't have to rewrite it. My degree is 5, so 5 minus 1 means 4. I'd have 4 maximums and minimums in some sort of combination. So I'd have 4 extrema. Okay. I do have an odd degree this time. 5 is odd, so that means my ends are going to be going in opposite direction. I do have a positive lead coefficient though. The x to the 5th is positive. So that tells me that the right end is going to be going up. So now how would that look if I have to have 4 curves in it? The left end has to be going down and the right end has to end up going up. So there's 1, 2, 3, 4 curves. There we go. Okay, so again, that extrema is telling you how many curves you have. And so here in this graph, I'd have 2 maximums and 2 minimums for a total of 4. So 2 minimums and 2 maximums. Now notice that for part A and for part B, I've had every single term accounted for. I had my 4, 3, 2, 1, and then my constant. 5, 4, 3, 2, 1, and then my constant. But for part C, I have x to the 4th. I don't have an x to the 3rd. I have an x squared, and I have an x. I don't have a constant at the end. You could say there's a plus 0 there, okay? But I'm missing terms in this one, okay? So, again, I have a degree of 4. So 4 minus 1 is 3, so that means I have 3 extrema. And I could even go a step further. I could say that I have an even degree, so I know that the ends are going to be going in the same direction. And I could say that I have a positive leading coefficient, so I know the ends are going to be going up. But if I was going to actually draw this, I'd have to verify it on my calculator. Because I've got those missing terms in here, it might be a little trickier to just kind of go up, down, and get it to fit these characteristics. Okay? So this one, part C, is kind of a special case if we're trying to think through it graphically or mentally to think what it will look like graphically. So if you have all terms accounted for, then you can do these characteristics that I was talking about over to the side, where you could figure out how many minimums and maximums of each you would have. Anytime you're missing terms, it's better to put it into your graphing calculator and verify it. If you do that, you're going to get 1 minimum and 2 maximums for your total of 3 extrema. Okay, so there's a picture of part A, similar to what we drew. There's a picture for part B. Okay, now we drew our rough sketch a lot more curvy than what it actually is, but that's okay. And then there's the graph for part C. So you actually only end up with 1 minimum. Okay, so again, this is a special case. Okay, now before we go on to your homework, I want to take a look at this extra example here. This is meant to get you thinking. This is meant to kind of connect everything that we've been doing and kind of think about the actual equations that are written for these functions with all these characteristics that we've been talking about. And this is really important because you might see it on a quiz or a test. Okay, so this is the type of thinking you need to be prepared for so you can do well on a quiz or a test. So if you've done all your homework and all of those concepts make sense, then you should be able to do this type of a question. So they want you to write an equation of a function that has the zeros of -1 and 3. And they have to have multiplicities of 3 and 1 respectively. So that means that the -1 has to have a multiplicity of 3 and the 3 has to have a multiplicity of 1. Remember, respectively means you go in the order that's given. So if you're going to write a function, let's just call it p of x, because all of our other ones have been called p of x. You could call it f of x if you wanted to as well. It's p of x just because it's a polynomial. Okay? Now you have to have a solution that's -1 and 3. So that means after you factored and you set your parentheses equal to 0, you got x equals -1 and x equals 3. So you set something equal to 0 and solved it to get -1. So that means you would have had x plus 1 in the parentheses. And again, you set something equal to 0 and solved it and got x equals 3. That means you would have had x minus 3 in your parentheses. So that's how you write the part with the solutions. That should be familiar and comprehensible. Now the multiplicity part just means we're going to put some exponents on each of those. Okay? So the first one has to have a multiplicity of 3. Well, that means we cube it. And the second one has to have a multiplicity of 1. So you could put a 1 in there for your exponent. Don't have to. There you go. There's your function. Okay? Now, what is the y-intercept of the equation? Now remember, the y-intercept is going to be that constant term that's added on all the way at the end. So if I took this function and I actually multiplied it all out, I'd have x to the something, and x to the something, x to something, x to something, and then all the way at the end, I would have plus some number. Okay, that's going to be your y-intercept at the end. And you can actually figure that out just from the function that we have written up above. Okay, now you get that intercept at the end by just multiplying or adding all of the constant terms together. So if I was to actually FOIL this whole problem out, I would have x plus 1 times x plus 1 times x plus 1 times x minus 3. Now you don't have to actually go through and FOIL this all out and actually find your y-intercept that way. There's a better way. Okay? Now you have this 1 and this 1 and this 1 and this 3, and they're all getting multiplied together. Okay? Now our solutions were -1 and 3. So what you'd have to end up doing then is you'd have to take the -1 times the -1 times the -1 3 times, because that's your solution 3 times, and you'd also have to multiply it by the 3, because that's your solution 1 time. So when you multiply all those together, you get -3. Okay, so that's your shortcut for figuring out what the y-intercept is. So your y-intercept is going to be -3. Now, if your y-intercept is -3, how can you adjust your equation so that it has a y-intercept of 6, or of -18, or of 24, or 1/2? So that means, how do you modify this original equation that we wrote up here so that now you have these values for your intercepts? Now it's a lot easier than you think. Basically, how do you change -3 to 6? You'd have to multiply the whole equation by -2. So you'd have to have a -2 out front of this whole equation. So it would be -2 times x plus 1 to the third and x minus 3 to the first. Okay, so that way after you multiplied all of the stuff in parentheses out and FOILed it all out, then you'd have to go through and multiply every single term by -2. Well, remember, at the end, when we multiply all the stuff in parentheses out, we end up with a -3 for our constant term. If I want that to be a -6, then I'd have to multiply everything through by a -2. So if I want to get a -18 for my intercept, I'd have to multiply by 6, because negative 3 times 6 is 18, negative 18. If I wanted to get a 24, I'd have to multiply the negative 3 by a negative 8. If I wanted to get a 1/2, now we're still going to multiply here. So think, what do you have to multiply by to change negative 3 into a half? That would be negative 1/6. So that means that you would put those terms, the 6 or the negative 8 or the negative 1/6, out front of your whole function. Okay, so think of those characteristics. Okay, if you really understand all of these graphing characteristics, you should be able to understand how they affect the equation for the function. So here's your homework for tonight. Definitely longer than the previous night's homework. It's a little choppier. Okay. Remember, I have all the solutions worked out in the binder in the classroom. Help yourself to some graph paper if you need that too. And if you have any questions, come on in and see me before school.